Why do we care about topological cyclic homology? What justifies introducing all that complicated machinery? Why would one be interested in learning all of that? What's the motivation? That's what I will tell you today. Hi, I'm Thomas Nikolaus from Mathematics Münster, and today we'll understand what our motivation for studying topological cyclic homology is. Basically, there are two main motivations that one could call for studying topological cyclic homology. One motivation is actually its close relation to arithmetic geometry, to crystalline cohomology and so-called symptomic cohomology. And I will not be talking about this relation today because in order to understand this relation, one has to first go a little bit into the theory. So later in the course, we'll sort of make clear where this relation comes from and how the computations match up and why this inspired the new theory of prismatic cohomology invented by Budd and Scholze. Today instead I'm going to talk about the historical first motivation for topological cyclic homology, and this motivation are so-called trace methods. So what's the idea of trace methods? So first of all we have to understand what the goal is. So R is going to be a ring throughout this lecture, and by ring I'll just mean associative, not necessarily commutative ring, say unital. And the invariant one actually cares about this ring is called Algebraic K-theory. And maybe say Algebraic K-theory groups. So what are Algebraic K-theory groups? So that's a sequence of abelian groups denoted K star R, where star is just a non-negative integer. So there's one abelian group for every number. And the point is that these are theoretically very important, and I'll tell you in a second a little bit why. But the downside about these algebraic K-theory groups is that they're really hard to compute, but very hard to compute, and not only compute but also structurally understand them. For example, the case of the initial ring, the integers, the algebraic K-theory groups are not yet completely understood. In fact, a lot is known about these algebraic K-theory groups of the integers. I mean, not that it matters for today, but let me just tell you that they can basically be computed in all degrees which are not, in all the odd degrees they can be completely computed, and in the even degrees, in fact in the degrees divisible by 4, they are conjectured to be 0. And this conjecture actually depends on a deep conjecture from number theory, the Kummer-Van Duyver conjecture. And in fact, this is equivalent to the Kummer-Van Duyver conjecture. So in some sense, this already has a close relation to number theory. But let me tell you a little bit more what the motivation are to care about these algebraic K-theory groups and how the relations go. So I guess the first relation, me being a topologist, that comes to mind is the so-called wall finiteness abstraction. That comes from the question when you have a topological space and you know it's a retract of a finite CW complex, then Wall studies the question whether this topological space itself is actually a finite CW complex. And it turns out there's an abstraction to that, the so-called Wall finiteness abstraction, and this exactly lies in the K group of the group ring of the fundamental group of that space. That's maybe the first appearance of algebraic K-theory in geometric topology, and then later actually in the famous S-cobordism theorem, also the abstraction for a cobordism to be trivial actually lies in an algebraic K-theory group by work of Whitehead and others. So, and in fact, nowadays there's a higher variant of that theorem, like the so-called stable H-cobordism theorem of Waldhausen, Jahan, Rogness, and that actually relates the diffeomorphism group of a manifold to some version of algebraic K-theory of that manifold, or like say the fundamental group or the loop space of that manifold. And that is actually one of the major tools to study diffeomorphism groups, or the homotopy type of diffeomorphism groups these days. Another reason why these algebraic K-theory groups play a role coming from geometric topology is related to the so-called Farrell-Jones conjecture, and maybe in its C-star algebraic guise, the Baum-Kohn conjecture. These conjectures are conjectures about K-theory of group rings, and in fact they have like very strong implications and applications in geometric topology. For example, the Borel conjecture, which predicts that an aspherical manifold is completely determined up to homeomorphism by its fundamental group. That would be a consequence of this Ferry-Jones conjecture, which is by deep work of many people now known for many groups. These are maybe instances in algebraic, in geometric topology where the algebraic K-theory groups come up. But they also, of course, they were invented by Grothendieck, in fact. Grothendieck invented the group K0 of rings in order to give a formulation of his version of the Riemann-Roch theorem. So that's basically where algebraic K-theory originated. So it has a lot of connections to algebraic geometry, studying of vector bundles and Riemann-Roch style theorems. It's also important if you study intersection theory in algebraic geometry, and finally maybe in number theory, for example, special values of L functions will lie in these algebraic K-theory groups, so they are important in order to study those. But instead of going on in this slightly obscure way about why we could care about those K-theory groups, let me say a little bit what these K-theory groups actually are. So here's the definition. So what is K0 of a ring? K0 of a ring is defined as follows. Well, what we want to do is we want to study isomorphism classes of finitely generated projective R modules. Over R, I guess R modules. And this is actually a commutative monoid because we have the direct sum operation, which allows us to add finitely generated projective modules. And this actually is kind of a little bit complicated to compute what this abelian monoid actually looks like in concrete examples. If I give you a concrete ring, it might be tricky to figure out. I mean, you have to classify all finitely generated projective modules, aka vector bundles over the associated affine scheme. And so the maneuver which sort of very often makes this easier to understand is that we take this abelian monoid and turn it into an abelian group. So we group complete it. So this group is just the group completion of an abelian monoid to an abelian group. So the initial abelian group receiving a map from this abelian monoid. You know this process from I guess, basic algebra, where you just take the natural numbers and turn it into the integers. It's just obtained by adding inverses. So that's the group K0, and then the higher K groups are unfortunately a little bit harder to define. So the higher K groups are defined as the homotopy groups of a space. Homotopy groups of the space in the sense of topological space, or homotopy type, of the space obtained by a group completing the category of finitely generated projective modules, projective R modules. So you see, I guess this is just a slogan at this point. This can be made precise by means of higher algebra. The idea is just not to pass to isomorphism classes, but take all morphisms of modules into account, take the full subcategory, and then there are ways, in fact, invented by Quillen, Siegel, and others, to make precise that one can consider this as a space and then take the group completion in the realm of spaces or homotopy types. And then you have to take the higher homotopy groups of the space, and in fact the space will be a spectrum in the sense of stable homotopy theory, and then we have the homotopy groups of the spectrum. Now you see, this kind of very homotopy theoretic nature of the definition is basically the reason why it's really complicated to understand these higher K groups. I guess for fields, say, if our ring is actually a field, then it's clear what K0 of R is, right? Because projective modules are just the same as vector spaces. And then a finitely generated vector space is just a finite dimensional vector space, and by basic linear algebra we know there's one for every positive integer, non-negative integer, and so this will be, the monoid will just be the natural numbers, hence the group completion will be the integers. So in other words, K0 of every field is the integers, but of course the higher K groups turn out to be very complicated already. In fact, in the very first paper where Quillen introduced these higher K groups, he also computed all of these for finite fields. So we know what the higher K groups for finite fields are, but already if we go away from finite fields, these higher K groups start to be very complicated. So, and that is what I mean by saying they are very hard to compute. I mean, somehow you have to get your hand on the space and somehow understand the homotopy type, or at least the homotopy groups of the space. And now this is where trace methods come in. So what's the idea of trace methods? The idea of trace methods, and that's like the motivation for this whole course that I'm going to talk about. Let me highlight again that this is not the only motivation that we have, but that's the motivation we opt for today. And the idea is that, well, while these K groups are very complicated, we would like to approximate the groups by easier groups, by more algebraic invariance. In other words, or maybe more computable invariance. Right? While these K groups are very homotopy theoretic in nature, it would be nice to approximate them by other invariants. And approximate is meant here in a very weak sense. Maybe for the moment, let's say approximate just means that there's a map into these algebraic invariants. And let me tell you a little bit more precisely what we will see, which invariants. So here are the algebraic K-theory groups K star R. And now the first thing that Achim will also explain a little bit better, there's the so-called trace map into the Hochschild homology groups R. Here's a map called the Dennis trace. And the reason that this is called the trace is actually has a lot to do with traces. That we'll see what the idea is in a second. Let me just say these Hochschild homology groups are something completely algebraically defined, and we have this map. And these Hochschild homology groups were in fact invented by Hochschild somewhere in the 40s. And later people have studied refinements of these Hochschild homology groups and of the trace. So what are the refinements? So there is one refinement called negative cyclic homology. It's a refinement of Hochschild homology due to Kohn, invented in the 80s. And there's another refinement in a different direction called topological Hochschild homology. These are also abelian groups. All of these things are just sequences of abelian groups for any ring. And then actually there's a somewhat of a common refinement of these two refinements called topological cyclic homology. So topological Hochschild homology was introduced by Böckstedt in the 80s, and topological cyclic homology by Böckstedt, Chiang, Madsen in the 90s. I think 94. And the fact is that there are trace maps into all of these groups. So in fact here is the master trace, the mother of all traces, the cyclotomic trace. And this factors all the previously defined trace maps. And that is what I mean by approximate by algebraic invariant. They are maps. And of course, let me explain in a second what approximate, I mean there's better theorems than just saying they are maps. And that's what I will explain now. So before I give you a precise result, let me first state some sort of slogan or meta theorem. We call it meta theorem. And the meta theorem says that the map cyclotomic trace is often, maybe I put it in bracket, close to an isomorphism. But in an ideal world, the cyclotomic trace would be just always for every ring an isomorphism. And then this would help us like tremendously. It would tell us that we can compute K-theory by this invariant. Of course, all of this would depend on being able to compute and understand this invariant, but the claim that I'm making implicitly here, and that we'll hopefully be able to back up during the course, is that this invariant can in fact be computed and understood much easier than algebraic K-theory. Unfortunately, this meta theorem is actually involves words like often and close to. And me being a mathematician, I don't want to leave this slogan or meta theorem on the board. So let me give you like a more precise installment of that meta theorem. Or in fact, I will give you 3 precise variants of this meta theorem. But let me just mention that for the rest of the course, this is not really relevant. This is just a motivation. And if you, I mean, I'm going to use concepts now which are a little bit more complicated, and I mean, nothing will depend on that. So the first thing to note, if you want to make a precise statement, is that algebraic K-theory, I mean, the way we introduce just depended on a ring, but pretty much like in topology, there's relative K-theory groups, K groups. So when I can compute define groups K star R comma I, where I and R is an ideal. So, and in fact, pretty much like in topology, where you have relative homology groups, these groups sit in a long exact sequence with the K-theory R, the K-theory of R mod I in this group. So in fact, if you know what a spectrum is, this is just defined as a homotopy groups of the fiber of the map of spectra from KR to KR mod I. And there's also variants for TC, so TC star R comma I defines the same way. And there's also K groups with coefficients. Groups with coefficients. Coefficients. So for example, I can take K-theory R with coefficients in the p-adic numbers. That's the variant we'll care about today, and this will just mean, I mean, it's basically just, I mean, if you took something like with coefficients in Fp, this would be roughly the mod p reduction of the K-theory groups, and this is roughly the p completion of the K-theory groups. And I say roughly because this is only true under finite generation assumptions. In general, it's the p completion of the K-theory spectrum and then take the homotopy groups. Okay, and also there's such a p-adic variant for TC with coefficients in Cp. And now I can tell you the precise results after cleaning the board. Okay, so the precise installments of my meta theorem that I want to walk you through today are the following theorems. The first is a variant given by Dundas, Goodwillie, McCarthy, very famous result. Dundas, Goodwillie, McCarthy, based on very important earlier work of Goodwillie in the rational case. And this says if I in R is a nilpotent ideal, so there is a number n such that the nth power of I is 0, then the trace, cyclotomic trace, from relative K-theory R comma I into relative TC R comma I is an isomorphism. So in other words, a more conceptual way of saying that is that the difference between K-theory and TC is nil invariant. And this is in fact very useful. So what's the typical application? I told you that these sit in long exact sequences with K-theory and TC of R mod I. So the application situation we want to use this for is that for some reason we understand K-theory as well as TC of R mod I. And we would like to understand K-theory and TC of R. And then you see the difference between K-theory of R and R mod I and TC of R and R mod I is the same. So it's under the assumption that we can compute K-theory of R mod I, TC of R mod I, and TC of R, this will basically give us a way of approaching K-theory of R. And that is actually exactly the situation in which this is used. But in fact, very often one needs a slight refinement of this result, and I guess there's a lot of refinements, but I guess the ultimate version was recently given by Clausen, Matthew Morrow. Clausen, Matthew Morrow, I was right. Morrow, if R is commutative and I complete. In fact, the result is a little bit more general if it's Henselian along I, but say it's I complete, then the same conclusion holds. Then also the map from KRI into TC star RI is an iso. For example, this way you can compute, if I is the ideal P and you have a p-adic ring, you can basically try to compute K-theory of a p-adic ring by means of its TC and its K-theory of the mod P reduction. And one consequence of this second theorem, and maybe the ultimate theorem that is known these days comparing K-theory and TC, is the following, also by the same group of authors in the same paper. They deduce from this that, in fact, if R is P-complete, so a p-adic ring, complete, then we have that actually TC is not quite isomorphic. Oh, and I guess I made a slight mistake. I forgot to put p-adic coefficients here. This is actually true with p-adic coefficients. Sorry, I apologize for that. But so here's a statement: if R is itself a p-complete ring and we look at TC with p-adic coefficient, then this is actually isomorphic to a certain version of K-theory called étale K-theory. So this is basically the étale. I mean, K-theory doesn't satisfy étale descent, but you can force it. You can étale sheafify K-theory, and then this is actually an isomorphism. And by famous conjectures in K-theory, like the Quillen-Lichtenbaum conjecture, now proven by Wierowodzki, we can exactly relate this to K-theory, at least in high enough degrees. Degrees higher than the dimension of that ring. Okay, that does it for my little motivation section. So the upshot of what I told you now is that if you for some reason care about algebraic K-theory, it might be a good idea to study topological cyclic homology. And in fact, a lot of computation done these days about, I mean, basically almost all of the modern computations are done by trace methods or by motivic methods, which we will not cover in this course, the motivic methods. And now, I guess the question remains why this is called a trace and what has this to do with trace and why does Hochschild homology show up here? And this will be explained to you by Achim now.
I'm Achim Krause from Mathematics Münster. As Thomas just explained to you, there is a trace map from algebraic K-theory to Hochschild homology. Where is that coming from? Well, let's first ask, what is the trace of an endomorphism abstractly? We will discuss that in the following setting. We let K be a field and R a K-algebra. And then we consider P to be a finitely generated projective module, say right module over R. So the trace should assign to every endomorphism of P some value. Since P is finitely generated projective, we can write this as tensor product of P with the dual of P. Keep in mind that R is not necessarily commutative at this point, so you have to be careful with left and right module structures. But here we're looking at homomorphisms of right modules, and so this copy of R still has a left R action, which we're using here in forming this tensor product. In general, you would then try to go to R by using a kind of evaluation map, which sends x tensor phi to phi of x. However, you have to be careful here. This is not necessarily well defined on this tensor product. Where does it land in? Well, let's look at what this relation here implies. This evaluation map would send x tensor r phi to r times phi of x, but it would send xr tensor phi to phi of xr, which, since phi is a right module homomorphism, is phi of x times r. And here you see, if r is simply associative, not commutative, these two things don't necessarily have to agree. We can get a well-defined map like this if we furthermore take some quotient of R, namely R mod the additive subgroup generated by commutators, i.e. modulo the relation that x times y is y times x, not in the world of rings, but in the world of just abelian groups. So we get a well-defined trace map from endomorphisms of P to this abelian group R modulo commutators. And this is called the Hattori-Stallings trace. Also observe that if R is in fact commutative, this relation doesn't do anything at all, and this is the usual trace. So, is there a more conceptual way of thinking about this? Well, in some sense, we have just considered R with both its left and right action by R, and we have identified those. So, another way of thinking about this is to remind yourself that a left R module is the same as a right module over the ring R op, where R op consists of the same abelian group as R, but is endowed with the opposite multiplication. This again defines an associative ring. So if we want to talk about the left and right action of R on R itself, then you can think of this as a bimodule structure. And following this line of thought, an RR bimodule can equivalently be considered as an R tensor R op module. And in fact, we have some freedom here. We can both consider it as a left R tensor R op module or as a right R tensor R op module by kind of reversing the roles these two factors play. In this language, what we're taking here simply is the following. This abelian group, R modulo commutators, is isomorphic to the tensor product that we get by base changing this R tensor R op module structure to R itself. If you work out the description of the tensor product as simply a quotient of something, then you will see that this amounts precisely to this relation. What we will see in the course is that we can actually derive this expression, and in fact the Hochschild homology of R relative K is precisely what we get. So the statement that Thomas was referring to is the fact, which we will also see maybe in this course, that there is a trace map called the Dennis trace from algebraic K-theory to the Hochschild homology groups of R, which refines this construction that we gave over here in the sense that in degree 0, where K0 is generated by projective modules, it actually takes a projective module to the trace of the identity, since HH0 is precisely this quotient of R modulo commutators in this case.
Okay, thanks Achim, and thanks Guy for watching. That does it for today, and starting next time we'll get straight into the matter and talk about details about the definition and the actual mass. I hope you're now motivated enough to follow this course and hope to see you soon.